goal is that of simulating the management of a reservoir. We keep the stream flow time series that we have generated in the previous homework, and you force the reservoir and you play with the opening degrees of the spillways, in the essence, and you generate a transformed time series of discharges downstream of the dam. In particular, the focus of the homework is about the interplay between hydropower production and flood control. So, simulation of management operations of the Corvo reservoir for hydropower production and flood control under different scenarios. In particular, we have the scenarios summarized here. The first one is about only hydropower production, so we don't care about maximum discharge downstream. In the second case, you have at the same time hydropower production and flood control downstream, which means that you care about the maximum discharge downstream of the dam. And there are different options with maximum level in the pool to allocate the upper portion of the reservoir to mitigate floods. And this can be done with a permanent maximum level or with a temporary maximum level, with and without meteorological forecasting, meaning that you have some time prior to the event to decrease the stage in the pool and meet the maximum level imposed to mitigate floods downstream. So that's what we are talking about. This is done to understand the interplay between management of the reservoir, natural stream flows upstream, and downstream regimes. Okay, this is the principle according to which the processes we deal with operate. So the reservoir balance, variability of the storage in the reservoir dV over dt, is equal to Q in minus Q out. So all the input fluxes minus all the output fluxes. In particular, we have a number of Q in and a number of Q out. As usual, we also have in the mass balance the evaporation from the lake, directly from the lake, and the precipitation over the lake in rainy days. In this case, we have a numerical model, so we also take into account direct fluxes on the lake, but we almost know that a priori these two terms, E and P, are smaller than the others. Okay, so the list of the terms is represented here. The unique input beside precipitation on the lake is the stream flow entering the reservoir, Q in. And this is what you get from the file stream flow in that you have produced with the previous homework. P is the precipitation on the lake, as I was saying before. This can be estimated using the file rain downscale that you have generated in the first homework. Okay, evaporation from the free surface is assumed to be positive only in days in which we don't have rainfall, because we assume that when there is rainfall, the net radiation is not sufficient to evaporate water from the lake. Q out is a kind of complex term, but because it is made up by many components, in this case, in particular, we have different spillways for different functioning of the reservoirs. So we have a minimum environmental flow spillway, something that is designed to deliver something downstream of the dam, QMEF. We have a spillway specifically designed for hydropower production, so taking the water from the lake and bringing that water to the power plant, which is QHS. We have some flow released downstream through the intermediate spillway of the lake, in the middle of the dam, let's say. And then we have two crest spillways on the top of the dam, that they act as overflow somehow. Okay? So we have different spillways operating at the same time in parallel, releasing water or removing water from the reservoir. Okay? Minimum environmental flow, hydropower production, intermediate spillway, crest spillway. Okay. Now, evaporation as I was saying before, evaporation is only active when precipitation is 0, and you can calculate this constant, this evaporation rate, using the Penman approach, more or less in the same way as you did for the computation of evapotranspiration in the second homework, with the only differences that I have been already discussing a few classes ago. Okay, this data, E0, the evaporation rate in not raining days, in centimeter by day, has to be placed in the input file, climate and basin. Of course, okay, this is a code, so we have an executable file as usual, then we have a folder input with a sequence of input files, and then we have a folder output, and when you run the code, all the output files are produced in the output folder, and you have to set up all the files in the input folder in a proper way so as to run the code. Okay, so one of these, now I will be explaining you quite quickly all the files that you have to set in the input, and in the input you have to give all the information needed, telling the code how big is the reservoir, how big are the spillways, how big is the catchment, how is the evaporation rate in this case, and so on. Okay, so from now on, 20 minutes or so, I will explain you all the information that you have to give to the code to make it function. Okay, so the first information I'm discussing is the evaporation rate. It is placed in the second line of the climate and basin file, and it is something that you have to calculate offline with the Penman approach. And the second information in this file is the catchment area. That is, I think it's already set in the example input files that you have in Moodle. Okay, this is about the property of the climate and the property of the basin forcing the reservoir. Okay, now spillways. We start with the minimum environmental spillway. Okay, we know the formula of the minimum environmental spillway because it is exactly the same formula of generic spillway. So we have a discharge coefficient, we have the area of the spillway, we have an opening degree, theta, and then we have the square root of 2 times the gravity acceleration times the head over the spillway, that is z, the elevation in the pool of the lake, minus the elevation of the spillway itself, z m e f. Okay, so the first 3 guys, discharge coefficient, area, and elevation, about the geometry of the spillway, you have to set these numbers in a file that is termed reservoir. And in the file reservoir, you place all the information about the geometry of the system. The opening degree of the spillway, instead, you have to set it in a different file that is called hydroelectric, containing the opening degrees of all the spillways. Okay, this is what I'm talking about. You see the 2 files, reservoir and hydroelectric. In particular, you see in the upper plot, in the upper screenshot, you see the file reservoir. You see in the second line, you have the area of the spillway, the elevation of the spillway, and the discharge coefficient of the spillway. A, Z, and C. In the hydroelectric file, instead, you have a number of information, mostly related to the hydroelectric production and the opening degrees of the spillways. I will explain this later. And as you can see in the second line, again, you have the opening degree of the spillway for the minimum environmental flow. In this case, 0.2. Okay, you have to set it somehow. Clearly, if you set 0 here, you don't have minimum environmental flow. The true minimum environmental flow released through this spillway depends on the stage, clearly, right? According to this equation. So clearly, the idea is to set it somehow, a relatively small value, so it has to get some minimum flow discharge downstream. And the idea is to verify that the minimum flow discharge is actually fulfilled. Okay, clearly, the larger this number, the more water you are releasing downstream through that spillway. If you release water through that spillway, you cannot process that water for hydropower production. Okay? So, in some sense, there is a trade-off. Okay. Let's move on. What about C? Okay, C is something that depends on the geometry of the spillway, as the hydraulic laws prescribe. In particular, in this case, how do you calculate the discharge coefficient for the minimum environmental flow spillway and for all the other spillways? You have in a document, a Word document that is provided to you, you have information about the discharge released through different spillways depending on the stage in the pool. So you have Z, height of the water in the pool, and you have discharge. So essentially you know the stage Y in this relationship, you know the area of the spillway, you know the discharge, and so you know the velocity, and so you create a plot where you have the velocity, discharge divided by the area on the y-axis, and you have the square root of 2 times the gravity acceleration times z minus z and if, so the head over the spillway, and you plot the experimental points that I give you in the document, and then you calculate the slope on the of the interpolating lines, and you derive the discharge coefficient. Okay, this way. I don't want to give you just the geometry and let you calculate that from the geometry. I just got the project, and according to the designers, there is this relationship between stage and discharge. So based on that, you back calculate the discharge coefficient. Okay. You do this for the minimum environmental flow of this spillway. In this case, clearly you have 4 tables: one for the minimum environmental flow spillway, one for the intermediate spillway, for the crest spillway, and so on. Okay. So the same operation will be done also for the other spillways. Okay. Second important output term from the reservoir is the stream flow directed, diverted from the lake for hydropower production. The formula is exactly the same as before. We have discharge coefficient, area, opening degree, and then we have the square root of the 2 times the gravity acceleration times the head over the spillway. In this case, clearly the level of the spillway is different than the minimum environmental flow spillway. So for all the spillways, beside tables of this type, you also have, I think it's the information here. You see, 230 meters. So you have also the height of the spillway for the different spillways. Okay. So again, discharge coefficient, area, and height in the file reservoir.dat. In the spillway opening degree is something that you have to manipulate because you have to run the model with different opening degrees for the hydroelectric production to see what happens. So this is something that you have to change to see the effect on the energy generated, the revenues from the selling of the energy, and the flow regime downstream. And this has to be changed in the input file hydroelectric, the same as before. Again, I provide you with screenshots. You see the reservoir file and the hydroelectric file. Again, in line 3, in this case, area, height, and discharge coefficient of the spillway for hydropower production. And in line 3 of the hydroelectric file, you have the weekend and the weekdays opening of the spillway for hydropower production. As you know, the price of the energy is different during weekends and weekdays, so this is why we have 2 different opening degrees during the weekends and during the weekdays. So you can differentiate the energy production during the weekends and the energy production during the weekdays. Okay. So these 2 have to be changed, trying different combinations to see what happens and to see what is the best solution from the viewpoint of the water manager. So from the viewpoint of the energy produced and the revenues from the energy selling. Okay. Intermediate spillway. Same rule, same information. Also in this case you have a document telling you something about the height, the area, and data to calculate the discharge coefficient, and you have to put this in the input file reservoir. In terms of the opening degree of the intermediate spillway, this is something that is not is an information that you don't have to give to the code, because automatically the intermediate spillway is closed almost in all the times. This is because physically we know that the intermediate spillway of the core reservoir is typically closed almost all the times. But to eliminate, to help reducing the stage in the pool to meet a maximum level bond to mitigate floods, the code automatically changes the opening degree of the spillway, of the intermediate spillway, during floods from 0 to 0.2. This is functional to reduce the stage in the pool and meet as quick as possible the maximum level that is prescribed to let the upper portion of the reservoir available to store water and mitigate floods. Okay? So this is something that you don't have to change. It is automatically set by the code itself. Okay? Okay, and again you see that in the reservoir file, in the third line, you have area, height, and discharge coefficient also for the intermediate spillway. And for the intermediate spillway, this information is taken from a table where you have stage and discharge exactly as this guy here. Okay? So here you find the area, you find the height, and you calculate with a plot of this type the discharge coefficient. Okay, when the intermediate spillway is activated, and some stream flow leaves the reservoir through the intermediate spillway, as a consequence, a message is reported in the output file report. So you see, intermediate spillway has been activated at the time step, and so you know that this happened if you want to check it. Okay? This file report is nothing more than a sequence of information related to what is going on. Typically, you don't have to check this report, but I mean, there are summary information about the type of simulation that you're doing. If you don't remember what you said to the code, here you can find a summary of the simulation that is going on and some other additional information about what happened during the simulation. Okay? This is an output, okay? This is an output of the code itself. So this is not an input file. It's something that the code produces to just keep track of what is going on. It is in this slide only because I'm telling you if the intermediate spillway is typically closed. So the discharge to that is typically 0. If this is not the case, you can check it in the report file that is one output of the code, because you get a message of this type. If you don't, this means that during all the simulation, the discharge leading through the intermediate spillway is 0. Okay, crest spillways. Okay, in the core reservoir we have 2 crest spillways operating at the same time, but with different heights and different shapes. Actually, to tell you the truth, one of the 2 is regulated. But for the sake of simplicity, in your homework, we assume that both the crest spillways are unregulated. Otherwise, you would have to play with another degree of freedom of the system, and the homework is already kind of complicated. Okay? So we have two different reservoirs, two different crash spillways in parallel. The first one of the two is the lower, I don't remember which. You have therefore two discharge coefficients. In this case, you don't have an area of the spillway, but you have a length of the crash spillway. And in this case, as you can see, the dependence on the height is no longer 0.5 but 1.5 because of the basic hydraulic rules for unregulated crash spillways. We have already discussed that. Okay, so we have two discharge coefficients, two lengths, and two heights of the two crash spillways. And again, you have to set these numbers in the reservoir input file. Line 1, 2, 3, 4, 5, and 6. Length and height of the spillways are reported in the file description of the color reservoir that you will find in the Moodle platform, together with the code. Okay, in one case you have discharge versus height, so a table of the same type that we have seen before. And for the second one, I'm just telling you the type of spillway, and based on that, you can go to the book of hydraulic engineering and river engineering, and you find the appropriate discharge coefficient for that. Okay. Again, when the crash spillways are activated, you have a message in the output file recall, just to know that you have reached the maximum regulation capacity of the reservoir. Okay, now the input file reservoir with the geometry is ready, and you have to keep it fixed. The file reservoir is this guy here. As you can see, you have the geometry of all the spillways and the hydraulic coefficients for all the spillways. And in the last line, you have the initial volume of water in the reservoir in cubic meter. If you set this number very large, you start with a very full reservoir. If you set it equal to 0, you start with a completely empty reservoir, which is not realistic. Okay? I think now you have the feeling about what is the implication for that. Can you remember what I said about soil moisture dynamics? Clearly, if you start with a very empty reservoir for the first, I don't know, 3 months, you will be doing nothing more than filling a bit the reservoir day by day. So probably it doesn't make any sense. It's just wasting of time. So maybe try to find out a reasonable value for that, making some attempts. Okay, not too full, not too empty. Especially if it is very empty, it takes some time before you can start the real simulation, right? All the time required to fill it, and this it's a lot of water, so this time can be 1 year or so. Okay. Okay. Now we move on. A second input file that you have to give to the code, it's the relationship between stage, volume, and area. Clearly, you have to know what is the stage for a given volume, because based on that volume, you calculate the stage, and then when you know the stage, you calculate the discharge released through all the spillways. Okay, so this is given a priori in this file. A discrete rating curve, that. It's a table of this type. You have 3 columns, and you have number of intervals, Z and B and area. So this is the number of lines that you have below this, and then you have height, volume, and area. So when the height is 215 meters, the area is 0 and the volume is 0, meaning that the height of the bottom of the lake is 215 meters. And then when you increase the height, you see you also increase the volume in cubic meter and the free surface in square meters. Okay? I think this is already given and you don't have to modify. Okay, I presume everyone knows that it's very important where and how you write things in input files for codes. Okay, so if I bring this stuff and I remove the first line, nothing works. Okay, because the code is ready to read a first line with nothing, and then a second line with nothing, and then a number that is used to think about how many things I have to read next, and then number. So if you say 46 here, you have to put 46 lines with 3 information each, otherwise nothing works. Okay? So don't change anything about the setup of the files, because otherwise nothing will work. The 2 basic things that you have to consider when you run the code is to maintain the structure of the file, same number of column and lines and all the information in the proper place, and the position of the files. But I will be talking about the position of the files later on. Okay, so this is the second input, discrete rating curve, relationship between height, volume, and area, necessary to calculate everything in the mass balance of the reservoir. Okay, proceeds. How can we calculate the proceeds? So for each time step, the code computes the energy, price, and the price is assumed to be fluctuating. It is in euro by kilowatt hour. I have assumed that there is a random component in the price, so there is some average with some fluctuations. Okay, here there is a formula. I don't care much about the formula. In the formula you can set up the mean price and the extent of the fluctuations. Okay, that's what is going on in this formula here. So PR weekend and PR weekdays are the mean energy price in the weekdays and in the weekend. The mean, the baseline. Again, how can you get these values? You can go online and find values about the price of the energy in the past and do some statistics. Okay, so it's very, very easy. You can take the last year or 2010 or the last 10 years and take averages. You will easily find information about the daily price of the energy through time in recent years. Okay, so this is what you have to do. This is, of course, this is an input, something that the code has to know to give you the answer. And then there is a random component, and the extent of the random component is modulated by this O max. This is a relative amount of the maximum fluctuation of prices. If this O is equal to 1, the random component has the same order of magnitude as the mean. If this O value is equal to 0, you only have a price that is constant and equal to the mean. Okay? Okay, so if O is equal to 1, this means that you can get plus 50% or minus 50% in that range. Okay, this is the value of O is actually not, you can try to do some simulations and you will realize that the actual value of O is not particularly important in terms of the output of the system. So if they are stochastic or deterministic, more or less you get the same result. Anyway, in this way you can simulate both the deterministic price, difference in the price between the weekend and the weekdays, and also random fluctuations through this random number x. Okay. Where do you have to set these guys? In the file hydroelectric. Lines 1, 2, 3, 4, 5, 6, and 7. So you have in line 6 the mean energy price in the weekday, the first, and in the weekend, the second. This is given in euros by kilowatt hour. And in the line 1, 2, 3, 4, 5, 6, in line 7, you have the maximum fluctuation in percent of the price. Okay. Search prices on the web, calculate the mean of weekdays and mean of weekends, insert the values here, and this is something that you can play with. If it is equal to 0, prices are fixed. If it is equal, if O is positive, you have fluctuations in the prices. Okay, then for each time step, the code can compute the power produced by the plant. As usual, the power is the product among the efficiency, eta, specific weight of water, gamma, the QHS, that is the discharge flowing through the spillway devoted to hydropower production, QHS, function of time, because it is of course function of the height of the water in the pool, times delta Z, that is assumed to be the net head available for energy production. Of course, okay, this is again function of the height in the pool. Okay, this is an important point. So for a given discharge, the higher the stage, the more energy you produce. Okay, so that's essentially why it is useful to set up a minimum level in the pool when you produce energy, because you avoid a drop in this term. Okay, this is the power in kilowatt, and then you can calculate the proceeds, summing up the power times 24, that is a conversion factor, times delta T, that is 1 day, times the price of the energy in that day. So every time you essentially multiply the power by the price, and you sum up for all the times, all the days in your simulation. How many days in your simulation? That's up to you. The longer the better, but that's also depending on the time that is required to run the simulation. So if you will have to run like 20, 30 simulations, very likely. So it is not safe to have 1 hour of computational time for each simulation. So try to reduce the computational time to like 10, 15, 20 minutes. Otherwise you get crazy. Okay, this is clearly dependent on the type of computer that you have. Okay, so you can calculate for different configurations the amount of money that you get from energy production this way, based on the level in the pool and the prices. Okay, to calculate this, actually you need to know the efficiency of the plant, eta. The efficiency is in the line 4 of the file hydroelectric, which is an input, of course. In this case, 0.7. As I was saying in the classes, typical efficiencies of hydropower plants are pretty high, so more than 0.5, 0.6. And you also have to place here in line 6, 5, the turbine height. And you will find the height of the turbines in the description file, description of the core reservoir that you will have available in Moodle. This is to set this term ZT in this equation and calculate the power based on the stage of the water in the lake. Okay, it's not enough because in some cases you will have to impose minimum or maximum levels, or you may have to impose controls, checks, on the maximum discharge released. So there is an extra file that is called static bonds, and this file is about constraint that you want to put on the simulation that you're running. Okay, this is a scheme telling you that there is one minimum level and one maximum level, but they are not operating at the same time. This is to avoid to constrain too much the simulation and create numerical instability. So you essentially have to choose to set a minimum level in the pool or a maximum level in the pool. What happens when during the simulation there is a minimum level bond and you're trying to empty the reservoir below that level? All the discharge spillways are closed so as to eliminate the output and avoid to go below the minimum level. What happens when you try to exceed the maximum level in the reservoir? The intermediate spillway and the hydropower spillway, they open to reduce the volume in the stage and decrease the stage in the pool. Okay. As I was saying before, you can have a complex interplay between minimum and maximum level depending on the scenario. So here you can find a summary. Only hydropower production without a minimum level, and in this case you don't have a static bond to place, so this file is disregarded. With a minimum level, in this case you have to place a minimum level in line 3 of the file static bonds, which is the last input file that you have to fill. So if we are talking about hydropower production, the main concern is essentially a minimum level. You don't want to decrease the level below a certain threshold, otherwise you decrease this Z term and you decrease this term here and you decrease the power and you decrease the revenues. Okay, that's the goal. When there is hydropower, so the ideal situation for some hydropower production, and this is what you actually see in the field if you go and check what is going on in reservoir stages during floods, the ideal situation for water managers is to have a fixed value of Z sufficiently high. Let's say ideally close to the maximum water stage that can be retained in the dam. Okay? That's the ideal situation. Unfortunately, nature doesn't work this way, so clearly in nature you have input into the reservoir that are stochastic according to soil moisture and stream flow dynamics that we have seen. Okay? In terms of flood control, what you want is exactly the opposite. You want that a certain value is not exceeded because you want to retain the upper portion of the reservoir to mitigate floods. So when you have hydropower production and flood control, you can introduce a maximum level in the reservoir. You have two situations. In one case, you have a maximum level bond always on, meaning that for the entire simulation, you don't want to exceed a given threshold. In this case, there is no constraint about the minimum level. So you only have a maximum level. In some cases, however, you can decide that you don't want to actually allocate the upper portion of the reservoir for flood mitigation every day, but you just do that in prescribed time periods. So in this case, you have a shift. In ordinary days, you have a minimum level, and then in flood alert days, you have a maximum level. So there is a shift between a minimum level and a maximum level depending on when you are. Okay? This is of course more convenient from the economical viewpoint because when there are no floods, you have a minimum level sustaining the head and increasing the hydropower production. Then when you have some flood coming in, you decrease the stage and you shift to the condition of maximum stage. But in 95% of the time, you still have a minimum level on, which helps you to increase the proceeds. Okay? Okay, so in the line 2 and 3, in this file static bonds, you have the maximum level and the minimum level. But you have more in this file, you have something about the maximum discharge downstream. So you have some information about what you have to do with the maximum discharge downstream. in line 4 you have a flag that is actually can be 0 or 1. If the flag is 0, actually nothing happens in terms of implications for management if you exceed the maximum discharge downstream. In this case, the maximum discharge downstream is 200 cubic meter per second, which is the real world value, more or less the real world value downstream of the Corlo reservoir. So if you have 0 here, this means that during the simulation you can release downstream more than 200 cubic meter per second and nothing happens. The only thing that you do is to check after the simulation if this happens or not. And so you can check out how many times the maximum stream flow allowed downstream was exceeded and why. If you change this number from 0 to 1, as you see in the right side of the slide, you are actually inserting a static bond on Qmax. So these 200 cubic meter per second values cannot be exceeded. And there are some management operations that when you realize that you're releasing more than 200 cubic meter per second, if you can, you close the opening degrees of the spillways so as to reduce the discharge downstream and try to fulfill the maximum discharge downstream that is allowable. Okay, so the ordinary operations of the reservoirs are modified, decreasing first the opening degree of the intermediate spillway, if it is open, and then, if it is necessary, also that of hydropower production. If this happens, again, you get a message in the report file where you can actually read if this was actually necessary or not. Okay. A few more input files, something that you have already produced in previous homeworks, in particular rainfall. So you have two input files, rain and rain downscaled. Rain is the daily rainfall and rain downscaled is the rainfall time series with a finer time resolution. These are used to set evaporation rate from the surface. So you need to know in which days it is raining or not, because if it is raining, the evaporation is 0, otherwise the evaporation is positive. And the rain downscale is also used to single out flood events in case you want to actually operate with a maximum level bond, not in the entire simulation, but only in specific time periods. Okay? If you want to operate with a maximum level threshold only during specific time periods, then you have to select the time periods. And this is done looking at the rainfall, so as to single out flood events from rainfall. Okay? It could be done with the discharge, maybe, so you can argue that it would be better to do it with the discharge, but in some cases the discharge coming in is not known, so I'm assuming that we don't know the discharge and we only know the rainfall. So clearly we know very well that it's not necessarily true that if the rainfall is heavy, also the stream flow is heavy. But this is typically what we have in the field. So that's why I'm using the rainfall to identify floods, because it's more realistic than other conditions. Clearly the code would be able to know also the stream flow, but we assume that this is not measured in the field. So it's like the code doesn't know this. Okay, I think here there is a shift to single out flood events, the rain downscale, and to set evaporation rate, the daily rain. Clearly, makes more sense to me. Okay, summing up, input files. Stream flow in, what is entering the reservoir. Rain downscaled, rainfall time series at time scale shorter than 1 day. Rain, daily rainfall, catchment and basin, evaporation rate and catchment area, evaporation rate calculated using Feynman, and catchment area given in the homework. File reservoir geometry that you have to fill based on the document about the Coral reservoir. Hydroelectric, containing information about hydroelectric management of the reservoir and some other stuff. Static bonds, minimum and maximum level, and maximum discharge downstream. Discrete rating curve, again, geometry of the reservoir. And this is all. Okay, so to make it functioning, you have to fix all these 1, 2, 3, 4, 5, 6, 7, 8 input files. Okay, some of them are already fixed, you don't have to do nothing, like discrete rating curve, I guess. Others, you have to fill them, in part or completely. Okay, for instance, the one about reservoir geometry or hydroelectric. Some of them, you have to play with them to change the setting and see the impact in the simulation. Okay, that's the idea. Of course, once you have fixed the geometry, that's it. You don't have to change it. But for instance, with the opening degrees of the hydroelectric spillway, you have to change it in hydroelectric file and try different numbers and look at different outputs that you will get from that. Okay? So there is a mess here in the sense that there are a lot of information, some files coming up from previous homeworks, some files that are already given to you, some files that are in part given. Some of them should be taken as they are forever throughout all the simulations, and some others have to be changed for different simulations. Okay? Additionally, you also have to give some information about what you want to do with the keyboard when you run the code. But these are just 2 or 3 information. The 2 or 3 information more that you have to give, it's about the scenario that you are running. Only hydropower production, also flood control, which type of flood control, and so on. Okay, I will explain to you this last part shortly. Do you have questions? Okay. You run the code, and I will simulate some run-up of the code in a while. You will get a sequence of files, very easy to understand. Streamflow out M3S and streamflow out CMD, containing streamflow time series downstream of the dam at the time step delta t, leaving the reservoir in cubic meter per second or centimeter per day. The conversion is very easy. It's a matter of units and the catchment area. Okay? Centimeter per day means specific streamflow by unit catchment area, length over time. Okay? To transform this number into volumetric discharge, you have to multiply by the area. Okay, daily streamflow out, same thing, but aggregated at the daily time scale. Volume and levels, the storage of water in the reservoir, and the stage through time during the simulation, from day 1 to day 5,000 or whatever. Free surface, the evolution of the area of the lake through time. And then this file, spillways opening, containing the opening degree of the spillways for hydropower production and for minimum environmental flow, and of the intermediate spillway at each time step delta t. Why I'm providing to you all this information, the message, the report file, and the spillways opening? Why? Do you have to plot them? No. Do you have to, I don't know, do strange things with that? No. The fact is that you have to understand what is going on in your simulation. Clearly not minute by minute, but in general terms. So if you are not understanding what is going on, you have to ask yourself, why I'm observing this process? Why I'm observing this streamflow duration curve downstream of the dam? what is the driving process for that. And if you want to understand what is going on, this can be very helpful, because you can realize, oh, during that event, the open individual spillways were large, small, zero, the crash spillway was activated, was not activated, and so on. Okay? So in this way, you are able to essentially keep track of everything happens in the code. And this should help you understanding what is going on in terms of functioning of the reservoir. Okay? Okay, so 5 output files. But we have additional analysis, and this is something that you typically have to look at. Okay, again, stream flow time series, very useful. You have 10 years of data. Can you plot it? Maybe not, it's a mess. But again, is this something reliable? Is it something that was observed in the past or will be observed in the future? No, it's not meaningful in a strict sense. It's only meaningful in statistical terms. Exactly in the same way as the input time series of discharge. So what I do is I calculate the probability density function of Q in, Q out, and the volume. So this is again a summary of the impact of regulation on stream flow regimes. You compare the probability density function of the discharge entering the reservoir and the probability density function of the discharge leaving the reservoir. That's the impact. If you compare time series, of course, you understand the functioning, but the global impact is summarized nicely by the difference in the probability distribution of discharge upstream and downstream. This is what the ecosystem perceives in the long term, actually. Okay? Then you have a file with the proceeds, generated power at each time step. You have this file report with all the choices that you did about the management and some auxiliary informations. You have a file temp with the volume and height of free surface for each iteration, if you need it. And you have a file flood alert that is generated only in case you work with the option when you want to consider the trade-off between hydropower production and flood control at the same time. Okay, I will be more precise about the flood alert things in a while. Okay, so input files, output files. And then you have the executable file. So the structure should be a main folder, H3. The main folder contains, I think, one folder input with 8 files, one folder output, empty at the beginning, and then we have, I don't remember how many, 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, okay, like 10, 15 files. Empty at the beginning, of course. Then we have the executable file, and then there is something like Corlo reservoir.doc with the information about the geometry of the system. Okay? So your task is going to be to complete the input files. You put your hands here, you complete what you have to complete, you derive the information, you set up all the things. Then you double click on the executable file. And when you double click on the executable file, you will get something like that. A black window asking you strange things. You have to answer. I will guide you through that in a while. And if everything is okay, when you are done, you will get 10 or 15 files or whatever in the output folder, and you have to take some of them and plot it and look it and understand what happened in the transformation between input and output, which means the transformation of the natural flow regime into some anthropogenic flow regime downstream of the dam. Okay? Questions? Okay. Now, this is the general picture. If you try to double click the code, this is what you get. So follow me on the screen. So reservoir management is supposed to be the name of the code. The first thing that asks you the code is the number of time steps for each delta t. In this case, I've set 10. I think delta t is 1 day. I'm not sure this is fixed or if you can change it or it is an information somewhere in the input files. I don't remember actually. I should double check. At any rate, the number of time steps for each delta t would mean the number of delta t that is used to calculate the water balance in the reservoir. If this number is large, the simulation takes you forever. If this number is small, you get numerical errors. I have to say that, shame on me, the number of the type of numerical scheme that is used is very, 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 very bad. It's the typical type of scheme that you, in books, you read, you don't have to do that. Okay? So it's a Eulerian forward. It's something very, very bad. This means that I store water and I calculate, I have some initial level and I calculate all the fluxes with the initial level, and then I go the next time step where all the fluxes have been calculated with the initial level. But if you are depleting or increasing the level, as you change the level, you also change the fluxes. And this creates some adjustment, of course. And if you don't do that with the numerical scheme, you get fluctuations that you will see regardless of everything in your simulation. It's my fault, you cannot remove it. Okay? It's a very bad numerical scheme. Okay, it's sufficient. Why I didn't change it? Because for our purposes, it's sufficient. You get some fluctuations, but I mean, you don't care. It's like, I don't know, activating a spillway and then deactivating the spillway, activating, deactivating, activating, deactivating. When you are close to the height of the spillways, something like that. Okay, so I'm putting 10 if you want to increase it, and you can make it with a computational time even better, okay? Then, the code asks you only hydropower production or hydropower production and plant control. If you answer H, only hydropower production. If you answer H plus F, hydropower production and plant control. Okay? If you say something else, nothing works. Okay, so the only two options, H or H plus F. If you say Q, yes, no, fuck, doesn't work. Only the power production, okay. No, if there is hydropower production, by definition, we don't have a maximum level, okay? Because we are only concerned with the minimum level. So, actually make this statement, providing that you choose only hydropower production, no maximum level, and then asks, do you want or you don't want a minimum level? And you can say no or yes. In this case, this is the basic scenario, only hydropower production, no minimum level, and I say no. Okay, only hydropower production without minimum level bound. That's your choice. Now I'm running, computing reservoir mass balance and so on. Okay. So this is the basic scenario, only the power production, no minimum level. What you have to do, the idea is to maximize the proceeds. Now you are the manager, you don't care about ecology, you don't want to cry about fish dying downstream of the dam, you want to maximize proceeds. Please remember, point something here, million euros, okay? So point to something, it's 200,000 euros, okay? So be careful, because these are large numbers. What is the goal? You try all the combinations of opening the grease during the weekends and during the weekdays. And you try to maximize the proceeds. So how do you build this plot to see what is the best combination for you? You keep the weekend opening fixed. And then you change the weekday opening degree, and then you plot the proceeds, and you build one curve, for instance, the blue one. Now, you change the opening degree during the weekends, you increase it or you decrease it, and you redo exactly the same thing, and you build a second curve, for instance, the green, and then you redo it again with a red, and so on and so on. And for any fixed opening degree during the weekends, you have an optimal opening degree during the weekdays. And then you have to select the maximum among the maximum. Okay, the very best among all the possible curves. If you want to do a surface, even better. It's an optimization with 2 degrees of freedom. So the real optimal solution would be a surface in 3 dimensions. Okay, these are slices of that surfaces. Anyway, I don't care. The only point is to find out the optimal combination. Okay. Okay. We should win. Now, and that's it for the first scenario. Okay. Be careful when you are exploring all the possible combinations. Okay. It's not necessary to run 1,000 simulations, but don't forget about possible combinations, because you have to be sure that the one that you pick is actually the best. 0.2 means a lot of money. Okay, so look also at the small scale details of the stuff. Okay, second scenario, only the power production, but with a minimum level on. So same story as before, but the answer to the last question is yes. Why? If you say why here, then the code goes to the input file static bonds and tries to read the minimum level from that file. Okay? So you don't have to give the number here. He is able to read the number in the input file. Again, is running. Okay, now the problem is complicated in the sense that my question here is, okay, the minimum level, it's up to you. There's no particular reason to select 260 meters or 255. So essentially, as a manager, you have now 3 degrees of freedom. Week and opening degrees, weekdays, opening degrees, and the minimum level. So this is a surface in 4 dimensions to optimize, very complicated. So I'm providing you a suggested solution. You keep fixed the opening degrees during the weekend, and you build, as before, curves in which you plot the proceeds as a function of the opening degree during the weekdays for different minimum levels in this case. And I'm telling you that this way you will get the optimal solution anyhow. So I keep fixed the opening degree of the spillways during the weekends, the one that you find before, and using that you only optimize minimum level and opening degree during the weekdays. Okay? Different curves corresponding to different minimum level. For different minimum levels, the optimal opening degree of the spillways for hydropower production is different. And then you have to find out the optimal combination. Okay, what I'm telling you is find out the optimal combinations from the viewpoint of the water manager. What I will be asking to you during the exam is why this happened. Okay, you have to understand why. And there are clear behaviors emerging from the simulations. And if you don't understand, you have to think why. Why it's not useful to increase further the minimum level? Why, if I increase the minimum level, the proceeds ... Okay? Okay, so this optimization problem with 3 degrees of freedom is reduced to an optimization problem with 2 degrees of freedom by setting the weekend openings equal to the optimal value that we found at the previous step. Okay. Okay, in this case you have to change the 2 opening degrees, and the 2 information that you have to play with are the minimum level in the file static bonds and the weekday opening in the hydroelectric file, the 2 guys indicated in this slide. In the previous cases, you had to play with the 2 numbers in the hydroelectric file here. Okay. After you do that, you select the optimal configurations in both cases. You look at the impact of the regulation on time series of discharges. How many years, how many weeks, how many days? It's up to you. Clearly, you cannot plot 10 years in one page. So you can decide what is the last plot. This is an example. You can focus on a single event to say what is, to understand what is going on during a single event, or 1 week, or 1 month. It's up to you. Okay. And then probability density functions. So the incoming flows PDF and the leaving flow PDF. You have 2 files with the same structure, stream flow and probability density function for natural flows, PDFQ, and for downstream flows, PDFQ out. To help you, I will provide at the end of the file, after the PDF that you can plot, mean, variance, coefficient of variation. Okay, I didn't talk about the skewness, so you don't have to care about the fourth information. Okay, so you can ask yourself, what happened to the mean, what happened to the variance, what happened to the coefficient of variation, and why. Okay, why? Why the variability decreases, increases? What is the mechanism? Okay, so this is the general trend, and then to answer to the question why, you have to go back and look at this plot. And to understand this plot, you have to go back and understand what is going on. Why the stage increases, decreases, what is the effect on the discharge through the spillway, what is the effect on the flow regime. Okay? Okay, now we have to face the other 2 scenarios with the flood control. And flood control is a little bit troublesome, so I have somehow engineered the system to make this delicate topic tractable for you. So let's start with real-world operational rules. So the water authority of the Brenta River, now is the water authority of all the rivers in the high Adriatic Sea, establishes that the water level in the Corvo reservoir must not exceed 252 meters above the sea level, except then during large flood events. This is a law dating back to 2002. I'm not sure if it was modified recently or not. Okay, so this law says that if the water level in the reservoir exceeds 252 meters above the sea level, the stream flow will be first flushed using the intermediate and the hydropower spillways, and if necessary, also the lateral crest spillways is used. When the level grows further, the highest crest spillway is also activated. So that's what we expect to happen during floods in the Corvo reservoir. So to simulate that, we answer to the first question about the scenario, not only not stating age alone, but H plus F, meaning hydropower, production, and flood control. Okay, in this case, if you select H plus F, the next question is not about the minimum level, but it's about the maximum level, because the code recognizes that you want to mitigate floods, so asks you, do you want some maximum level then? Because this is the only chance that you have to mitigate the flood, in agreement with the law that is actually holding over the behavior of the core reservoir. And you have two options. We start with the simplest. Maximum level bound active only during flood alert periods, or maximum level bound always on? And we answer A, always. Okay, he says, okay, hydropower production plus flood control with maximum level bound always on. No minimum level bound then. Computing reservoir max balance. How this choice impacts the code? If there is a maximum level bound, like in this scenario, when the level in the reservoir tends to exceed the maximum level, the code changes the opening degree of the hydropower spillway automatically and equal to 1. I try to process all the water that I can, then, provided that by law I cannot exceed this threshold. If this is not enough, we also open the intermediate spillway, and we eliminate some water with an opening degree of equal to 0.2. If this is not enough, clearly what happens is you try to fill the reservoir, but the intermediate spillway is pretty large, so I presume that with an opening degree of equal to 0.2, you are able to deliver downstream a lot of cubic meter per second, and this doesn't happen. Okay? Okay. Okay, so now you can have a comparison. Only hydropower production or hydropower production plus flood control with a maximum level. Different stream flow distribution downstream. Different impacts on the flow regime, but also different proceeds. So, impact on time series of discharges and impact on the proceeds. The question about the impact on the proceeds is particularly relevant to me because, of course, the water authority says to the energy company, okay, you cannot exceed the level 252 meters. And now the question is, okay, they get some money for doing that. So they are paid for maintaining the level in the pool below a certain threshold. How much? So, of course, I don't know, maybe there are political agreement about that, but the scientific question to that would be to run a simulation of this type to analyze the difference in the proceeds. Why is going to be not convenient for the electricity company to have a maximum level because the company cannot exploit all the reservoir. So it's like having a smaller reservoir, smaller stage, smaller head, smaller regulation capacity, and this in the end produces smaller proceeds. Okay, also in this case, you are, of course, encouraged to look at the time series and the PDFs like this, but also to understand why this happened and what are the consequences in terms of proceeds. Okay, this homework is not about having a correct answer and wrong answers. It's about understanding the link among processes and consequences. So the interplay among flow regime, management rules, and downstream regimes, proceeds, and effectiveness in reducing floods. Okay, so form, function, nature, and anthropogenically disturbed. Okay, last scenario, or I should say two last scenarios. The most complicated thing. Flood control rules only in specific periods when a flood is coming. In all the other time periods, only hydropower production, including a minimum level bond. Okay, so you answer to the first question H plus F, meaning hydropower and flood control. You answer P to the second question, meaning I don't want a maximum level bond on every time, because I have right now seen that it's very, very expensive, because the proceeds are now much smaller. So maybe it's useless, because most of the time we don't have floods. So we select P here, meaning that we have a shift in the simulation between maximum level and minimum level, as detailed in the screen. When there is flood alert, maximum level bond on and no minimum level. In the other periods, minimum level bond on and no maximum level bond. So during floods, maximum level. In the other periods, minimum level. Okay, now you have options. Now the next question is, how can we identify floods? And the idea of the homework is to use the rainfall for reasons that I have already discussed before. In most cases, it's not reliable to assume that you have a discharge measurement station right upstream of the lake, especially in Italy. It's not very frequent. It could be strange, but in Italy it's always never the case. So I'm using precipitation data to simulate stream flow, even though I know that this is not going to be effective. So to identify floods, I'm using a precipitation depth accumulated over 2 days. So if the precipitation depth in 2 days exceeds a given threshold, then this is a flood. And I shift from a minimum level bond to a maximum level bond, releasing water from the reservoir, if it is necessary, of course. Okay? So the next question here is about the threshold rainfall depth that is necessary to trigger an event in centimeters. So in this case, 9 centimeters of water, 90 millimeters over the catchment. Okay, the second question is about having or not having a meteorological forecasting system, and I will tell you what is going on in the next slide. Okay, how we can single out a flood event? The code computes the accumulated rainfall in all the groups of 2 consecutive days during the simulation, where the code reads this information in the file rain. The file rain contains the daily rainfall. Okay, so it aggregates 2 lines in the file rain, and it computes the amount of rainfall in 2 days. When the accumulated rainfall is greater than a threshold, the threshold that you set here using the keyboard, an event begins. When the accumulated rainfall in 2 days is then less than 0.2 centimeter, the event ends. Okay? When you start, and you have now to decide when it ends. So to decide when the rainfall event ends, you have a minimum threshold of 0.2 centimeter, meaning that now you have to wait that you have essentially no rainfall for 2 days. When you have no rainfall for 2 days, the event ends. Okay? That's how the code computes the beginning and the ending of a rainfall event. Okay, you see an example here. Here there is the rainfall time series, daily rainfall. Every cell is a day. You start, you compute the rainfall in the first 2 days. The overall rainfall is 1.8 centimeter below the threshold. In this case, the threshold is 9. So no rainfall, no flood event. Then you compute the sum of the second and the third, 11.3, begin, then 10 and 0.1. Okay, again we are inside the event, and then 0.1 and 0, the sum is 0.1, below the threshold 0.2, this means that now we have the end of the event. Okay? This is done to eliminate moments inside a rainfall event where you have a reduction of rainfall. Okay? So to decide that you have the end of the rainfall event, you have to wait that there is no rainfall for 2 consecutive days. Essentially no rainfall for 2 consecutive days. Okay, and then there are 2 options, with and without a meteorological forecasting system, meaning that we have 2 options. In the first option, we can look at the rainfall today, only this evening. Okay, so this evening we know the rainfall today and the day before, and we can calculate the threshold, we can calculate the cumulated rainfall, and we can compare the cumulated rainfall with the threshold. And today we state that the sum exceeds the thresholds, meaning that today the event starts. And today the event starts means that now I start reducing the level in the pool. Now. But we got 2 days of rainfall. Okay? In the second option, in the first option, I assume that I have a meteorological forecasting system and I can trust the amount of rainfall using weather forecasting. In this case, I'm able to know what will be the rainfall tomorrow and the day after tomorrow now. Meaning that now I know that in the next 2 days I will get a flood, and I start now to decrease the level because now I switch from minimum level to maximum level. So today I start decreasing the stage in the pool because I want to accommodate the water coming in the future through the floods. Okay? So what is the difference? Is that if you have a meteorological forecasting system, you have more time to reduce the level in the pool before the real flood comes in. If you don't, you can try to do that, but most likely you don't have the time necessary to actually do it. Okay? Here you can find the details. If you do have a meteorological system, you know that an event is going on, is going to begin, and you can start flood alert operations, meaning maximum level on, 2 days before. Okay, and this is what is going on. So if this is the discharge, based on the rainfall, you can single out, you see, a begin of an event essentially during the peak without meteorological forecasting systems, or 2 days before with some meteorological forecasting system. Okay. Questions? Is it clear? Okay, so in the last scenario, which is hydropower plus flood control, maximum level not all the time but only during periods, you have a maximum threshold rainfall depth that you have to set to identify floods. The smaller the threshold, the more event you will be identifying. And you also have 2 options, with and without a meteorological forecasting system, meaning that you know in advance the rainfall or you don't. And if you know in advance the rainfall, you are able to start the operations necessary to meet the maximum level bond 2 days before. Okay? That's it. If you work with a flood alert operation, you also have a flood alert file as an output telling you all the events that were identified based on the algorithm, and you can actually double check if these were actually true floods or not. what is the driver? I mean, why in certain cases yes and in other cases no? This clearly depends on the initial moisture state of the system. If you have 9 centimeters of rainfall over a very wet catchment, most likely you will get a real flood. But if you get 9 centimeters of water after a drought, and the soil moisture in the system is very, very low, 5 out of 9 centimeters will be used just to fill the soil water deficit created by evapotranspiration. Okay? So that's why I'm telling you, maybe try to have a look at the correspondence between what the algorithm based on rainfall identifies and what is the real effect. So, okay. I think this is the last slide. So summarizing, hydropower production with maximum level bond for flood control always on versus hydropower production with a maximum level bond only during floods, with and without forecasting. Increase of proceeds should be because most of the time you have a minimum level on that helps you increasing the proceeds. Effects on the highest flows downstream of the reservoir, is this actually effective in mitigating the floods? The question, is the flood control effective? Is the question stupid or trivial? No. Remember that two things. The first is that you are identifying floods only using rainfall, which means that in some cases you think you will get a flood and maybe it's not the case. The catchment is able to accommodate the rainfall that is coming in, increasing the soil moisture. Okay? And the second, which is actually very similar to what happens in the real life. And the second question, and the second point that is relevant to this question is, take a look at the size of the spillways and the discharge that you can eliminate through the spillways. These are very, very big, like 25 cubic square meters of spillways. And they can release like hundreds of cubic meter per second. Why I'm telling this? Because in some cases, to meet the maximum level of the reservoir, you suddenly decreases the stage in the reservoir, opening the grills of the spillways, and you create an artificial flood downstream. So it's very interesting because, and this is actually how the reservoirs work in many cases. You don't know what is going on in the future. And to change the level in the pool kind of quickly enough, in a couple of days, you have to release a lot of water downstream. So there is a significant chance to create floods, artificial floods downstream, just to meet maximum level criteria in the pool. And it's not necessarily true that when you shift to the maximum level in the pool setup, you actually will get a flood. This depends on the true rainfall that is coming in and the interaction between rainfall and soil moisture dynamics. Something very complicated to manage. Okay, so again, what is the impact of different management criteria on the stream flow distribution, probability density function of the discharge downstream, why this happens, what happens to the mean, to the variance, to the coefficient of variation, and so on. Okay? That's it. Do you have questions? Okay, if you go to Moodle, you will find a system of folders of this type, with the executable, the Word file, and the two folders. I think the output folder is empty, and the input folder is partially filled with files. I think they are all of them, but most of them have to be filled by yourself.
Dobbiamo lavorare in posizioni precise del computer.
You can put your H3 folder everywhere, but inside H3 everything should be organized this way. Okay, so you can work with this guy on the desktop, and it works. The only thing that The executable is looking for this folder, and inside this folder we'll create a file. The executable is looking to an input file folder inside which wants a certain number of files, and inside each file it looks for a certain number of information, and everything should be properly adjusted, otherwise it doesn't work. Okay? For the expert users, if you have problems running the executable using Windows, this way, double click, you don't see the error message because the black window closes. Okay? If you want to double check, or typically the answer is wrong file, wrong position, wrong information, inconsistent information. I've set 40 lines and I have 39. I have deleted one line. One information is missing. But if you want to double check and see what happens when you get error messages, you have to run this using the MS-DOS window from the command prompt. This is for expert. It depends on the type of system that you have. Anyway, there is a system to run this code in a different way and have the chance to look at the message. You have to use the MS-DOS command prompt. That's what you have to do. And in that case, you have to tell to the computer, please go to the H3 folder and then run this file with this name. So in that case, where you place the H3 folder, it matters. Only in that case. Okay, see you on Thursday.